on land and in the air. Loctite, the conquest of inner space. Ever since man needed to harness power, many methods have been devised to combine individual parts into assemblies. Engineers everywhere have exercised their ingenuity to design and produce cotters and threads, keys, screws and pins in a variety of shapes and sizes. As machining skills advanced, more complex devices were created. Splines, circlips, knurled shafts were also developed, all with the same simple objective: to join parts together and keep them together. But despite their diversity, all these methods, whether ancient or modern, have one thing in common. They have to be machined to an expensive precision. A simpler method of joining parts together, of course, is to force them together. But paradoxically, this simple method demands even more precision and costs even more money, because precision takes time and often has the byproducts of scrap and waste. Consider this pin and collar. To achieve an H7 press fit to British standard 1916C, both parts must be machined to give an interference of 0 to 4 thou. Forcing these parts together generates stresses which can cause distortion and premature failure. Parts may have to be heavier to withstand the stresses and may need reworking to remove the distortion. This is the Westland Lynx, which on the 11th of August 1986 gained the world helicopter speed record for Great Britain by flying at 249 miles per hour. For helicopter pilots, the distortion created by mechanical retention made it difficult to obtain the required joints of low friction with low backlash. Every Lynx helicopter produced at Westland's Yeovil factory has some 200 spherical bearings in its control linkage, serving the cyclic and collective sticks, tail rotor pedals and main rotor hydraulic jacks. Originally, these bearings were secured into steel and aluminium housings by ball staking in a press. But this wasn't satisfactory, as explained by Westland's chief mechanical designer, Jerry Martin.
The mechanical method of retaining the bearings caused the breakout torque to vary considerably. The wide operating temperature and humidity range increased this effect. Now, because of the length and complexity of the control linkage between the pilot stick, the main rotor, and the tail rotor, with its many bearings, any increase in breakout torque could affect the operation of the automatic control and place undue load on the pilot. In fact, we measured the dynamic torque of some stake bearings and found in early testing that 34% exceeded the specified loading of 0.6 ounce-inches. Consequently, it was decided to replace ball staking with a Loctite retaining adhesive.
The retainer is now applied to the bore of the housing. The bearing is slipped into place, and simple plastic cups are used to centralize the bearing during the 15 minutes required for the adhesive to gain handling strength. This used to be a much trickier operation during staking, because the fitter had to ensure that the housing remained proud of the bearing by 20,000ths of an inch. The simplicity of the adhesive method, chosen to remove the risk of the pilot's controls binding, thus gave a bonus. Fitting time was reduced from 10 to 15 minutes to around 2 minutes for each bearing. Since every Lynx has approximately 200 bearings, that means a saving of 26.5 hours per aircraft. And these advantages, it's worth noting, were not at the cost of modifications. Tolerances of bearings and housings, which give a diametrical clearance of around 2 thou, remain the same, allowing a simple slip fit of the bearings. But when you're building helicopters, you can't take chances. It took 2 years of tests under humidity, contamination, temperature cycling, and vibration conditions before the decision was taken to use Loctite for the flight control bearings. Remarkably, however, the easy, stress-free adhesive method is stronger than the interference fit, and that's a claim which is easy to prove. Consider the pin and collar forced together earlier. It needed a press load of around 0.8 of a ton to push the pin into a collar 1/4 thou smaller. Yet when we turn this press-fit assembly around to push the pin out of the collar, it requires a smaller load to separate them. Now take the same pin and collar, but give them a diametrical clearance of 10 thou. Apply a Loctite retainer, and slide the pin into place. When the retainer is cured, give it the same press-out test. And as you'll see, it needs double the load to separate the slip-fitted parts. A more practical proof of this strength can be seen at the British Sidak factory in Wigton, Cumbria. Here, a Loctite retainer, used on rollers to produce a packaging film, has replaced a laborious 8-hour process of turning, boring, welding and machining. First, the 2-inch bearing shaft is fitted into a trunnion. Previously, this assembly was machined from a 4.5-inch bar of steel, generating a lot of expensive swarf and taking 1.5 hours of lathe time. Now, shaft and trunnion are made as individual pieces with a 5 thou clearance. In 15 minutes, shaft and trunnion will have fixtured. In 45 minutes, they will have handling strength. In 3 hours, they can be placed under full load. Long before that time, the trunnion and shaft assembly will have been slid into the roller. In pre-Loctite days, the roller would have been heated to enable the trunnion to enter, and they would have been welded together. Now there's a 3 thou clearance between trunnion and roller to ensure an easy slip fit. In a few minutes, assembly is complete. Yet tests prove that that simple joint will withstand a load exceeding 50 tons. Incidentally, parts don't have to be massive before you gain the advantages of a slip-fitted assembly. The dowel pins used by the Ertling division of W&T Avery in the balance levers of precision weighing machines are only 4 and 6 millimeters in diameter. But speed in assembly and strength in service are just as important to engineers who produce sensitive balances. The reason for the strength of the slip fit can be seen with a 1000 magnification. This shows contact between the parts is restricted to high points. Often this is only 25% of the interface area. Over the remainder there is a gap, a hidden inner space. For centuries, engineers have striven to conquer that inner space by improving surface finish and reducing tolerances. Actions which, as you can see from the graphs, cost money. A lot of money. And yet, protracted machining isn't necessary. Stronger assemblies can be obtained from relaxed tolerances and rougher surfaces simply by using a liquid adhesive which will flow into and fill the inner space. Because a Loctite retaining adhesive is anaerobic, it'll automatically self-harden when deprived of air to provide total contact between the interfaces. The resultant integrated assembly will resist shock loads and vibration, and is leak-proof. This is an advantage of adhesive retaining which was just as important as strength to Perkins engines. Here at Peterborough, the company has set up a new multi-million-pound production line capable of building 80,000 of the new Prima diesel engines every year. As you'd expect from the world's first high-speed direct-injection diesel engine for cars and light vans, this power unit has many advanced features. A combustion bowl in the piston, for example. Mike English, a senior production engineer who played a major role in setting up the Prima line, showed this to us.
One of the advanced features that we've got on this engine is the piston bowl here, combined with the porting within the engine cylinder head, gives us an optimum performance and fuel economies previously unheard of in other diesel engines. In addition to the engineering features of the engine, this engine has also been designed for manufacturing. It incorporates a number of advanced sealant techniques where traditional gasket design has been replaced by anaerobic sealants. The first instance is the backplate here. We put the backplate simply onto this machine and the formed in place gasket is laid directly onto the component. Similarly, we have replaced the conventional gaskets with anaerobic sealants on our water pumps. The Perkins Prima engine is designed to give up to 100,000 miles between major service. In order to ensure the engine has a leak-free life, we use sealants in our assembly process.
Perkins achieved this objective of a leak-free engine by using a retaining adhesive. A bead of retainer is applied by a semi-automatic handgun to the passivated steel of the oil drain. This is then simply slipped into the cast iron cylinder block and aligned. The fitting of the dipstick tube is just as quick. Both parts are then completely sealed. This is an advantage which no other retaining method can give, and one which can eliminate a major cause of wear. Slight movements under load shear off the peaks making the contact between the interfaces of a force fit. Consequently, parts loosen and fretting corrosion takes place. This shaft from a vibrating screen, for instance, ended up 25 thou oval. The effect of this wear caused the shaft to hammer its 14-inch roller bearings into scrap after only 3 months of service. Repaired as an emergency measure with a high-viscosity Loctite retainer, however, this shaft was still in service at Erith, Kent with Pioneer aggregates 2 years later without further damage to its 600-pound bearings. Fretting corrosion was eliminated and years of wear had been taken up by a single 50 ml bottle of Loctite retainer. Long trouble-free service is also expected by the millions of car owners who use Delco windscreen wiper motors, which is why in 1975 Delco products replaced a press fit with a Loctite retainer to secure commutators to armature shafts using fully automatic equipment. The armature assemblies move down the line to the applicator where a measured drop of Loctite retainer is applied to the shaft. The commutators, fed from the hopper above, are slid into position. Within a few minutes they have fixtured and are ready for the next manufacturing process. If we looked at the motor driving this vibrating hopper, a similar shaft retaining application could probably be found, because a major maker of such motors, Grantham Electrical in Lincolnshire, have also changed to a Loctite liquid retainer. Originally, mechanical methods were used to retain the shaft in the rotor, the bearings and their housings in 4 sizes of Invicta vibrator motor. Today, all these parts are retained with an adhesive. The shaft is now slipped into the rotor because tolerances have been opened up to give clearances of 1 to 3 thou. Bearings are also slid into their housings. During service, those bearings will be pounded by centrifugal loads of up to ½ a ton. Bearing sleeves are also retained with a Loctite retainer on the rotor shaft, and the sleeves are then skimmed to size. After the bearings have fixtured in their housings, the housings are retained in the stator frame by the same simple method. Previously, these would have been drilled and tapped to be locked by set screws. And the shaft would have been pressed into the bearings in a race. Today, the motor can be completely built on the bench. Assembly is faster and the motors cost less. Grantham Electrical report that the adhesive retaining methods that they've been using now for 5 years have significantly reduced the cost of a vibrator motor. The company, in fact, achieved what it set out to do. But as you'd expect, it didn't accept Loctite on trust. Before using a liquid retainer on the production lines, it carried out many practical tests of the adhesive's capabilities, including that of establishing what force was needed to separate retained parts. This emphasizes that adhesive retained parts can be dismantled for servicing by normal methods. A variety of retaining adhesives with differing strengths and properties are available to match all manufacturing and service needs. For example, an oil-tolerant grade of mild strength would be used on the Perkins Prima line for as-received parts under light loads. A stronger grade would be used by the bore coater on another line in the Perkins factory. Loctite retainer is applied by these centrifugal sprays, which descend into and retract from the block to simultaneously coat all bores with a high-strength retainer. This is a fully automatic operation when the block is in position, which ensures a predetermined quantity of adhesive is evenly applied. The task of the retainer is to supplement the press fit of the liners into the diesel engine block. And that application highlights another function of Loctite retainers. They can strengthen an existing interference fit. Hence, assemblies can be uprated to withstand higher loads without the need for modifications such as tighter tolerances or larger engagement ratios. Back at Westland in Yeovil, we can see another example of a Loctite adhesive strengthening mechanical retention. The bronze bush supporting the main rotor flying control spindle at the top of the rotor gearbox is shrink-fitted into a cast aluminium housing. Fatigue tests showed that the bush loosened due to the different expansion rates of the metals. Coating the bush with a retaining adhesive before fitting it into the heated housing cured this looseness. As the housing cools, the film of adhesive is placed under compression, enabling it to cope with any future differences in expansion. Quinton Hazel also supplement a heat shrink with Loctite, enabling a gravity cast pump body to withstand an interference fit and raising push-out force to 5 tons. Of course, not all applications are high-load, high-tech or high-spec. This stainless steel plumbing from Lancashire Fittings may not seem like innovative engineering to the public, but its use of adhesives to join and simultaneously seal is arguably a more novel application than the retention of the steering bushes and king posts on thrust 2. And to the FTL company in Leeds, the ability of a Loctite retainer to permanently bond brass ferrules in flexible stainless steel cables for public payphones wins as many plaudits as the retainer used to secure bearing shells in high-speed motorcycle engines, now standard practice wherever racing stresses have to be endured. The exotic, however, will always capture more interest than the everyday uses of the liquid retainer. But by commanding attention, these more notable examples of the Loctite conquest of inner space help to emphasize a modern engineering principle, which is that design and production engineers who make products which must perform reliably under stress now retain parts with Loctite. Every engineer who's ever had to contain liquids or gases has known this moment. The time when a gasket fails. As our roads and floors emphasize, gaskets fail in their thousands, which means that thousands of replacement paper gaskets, fiber and cork gaskets have to be stored, lying idle, expanding inventories, tying up capital, just waiting for failure. And there's a lot to cause gasket failure. Differing thermal expansion rates can create hostile stresses causing fretting, which generates bolt loosening side loads and crushing loads, compressing and relaxing the gasket. Consequently, bolt clamp loads slacken. Fluctuating pressures and sudden surges can produce the same results, which attempt to force apart flanges and squeeze out the gasket. A gasket which may already be weakened by the attacks of corrosive material it has to contain. And a gasket's enemies aren't only from within. Impact, vibration and torsion generated during service also induce the stresses and micro-movements which cause gasket failure. The tremendous torque loads, for instance, placed on the transmission of Terex earth movers cause tiny flexing movements between the differential and the axle casing. Result, a leak. Terex engineers stopped that leak with one simple change. They threw away their gaskets and replaced them with a liquid, which simultaneously sealed and strengthened. In the Leicester laboratories of Rank Taylor Hobson, a TallySurf 6 reveals the fundamental machining defect which enables strengthening and sealing to be combined. The operator of this computerized metrology instrument first selects a 2000 magnification, and then he actuates the sensor to show that a milled flange with a surface finish of 20 microns peak to valley really has numerous surface deviations. Even a setting of 1000 magnification reveals, in the three-dimensional view, as many peaks and valleys as the Alps. A gasket compressed into these surface irregularities will certainly block leak paths through those valleys. But it can do nothing to stop leaks caused by movement between flanges. The Loctite liquid sealant, however, can do both jobs, and has done so on all Terex wheeled earth movers for the past 8 years. Instead of sealing by compressing a non-structural malleable material, a Loctite anaerobic sealant works by flowing into the irregularities of both mating faces as the joint is assembled. Leak paths are sealed as the sealant quickly cures into a tough plastic which forms a definite structural link between the flanges. And note the metal-to-metal contact of the flanges. There is nothing between them to shrink, abrade or relax, so clamp loading is constant. The separate parts become one rigid unit with greater torque transmitting capability. To companies such as Jaguar Cars, aiming for clean, dry machines requiring little maintenance, the advantages of using formed-in-place gaskets instead of pre-cut gaskets have proved irresistible. To employ them on production lines, however, demands automated methods of application. For example, fitting a Loctite gasket to the camshaft carrier of V12 engines only needs the push of a button. The nozzle of this XY coordinate unit follows a pre-programmed path with a constant speed control, ensuring an even bead of sealant. To form gaskets on smaller parts, Jaguar screen print gaskets. The method deposits just the right amount of sealant to give main bearing caps a perfectly formed and accurately positioned gasket. This method is also used to simultaneously print gaskets for 4 water cover plates. Because the anaerobic Loctite sealant cannot cure until the parts are assembled and air is excluded, this mass printing of gaskets doesn't result in waste. Left in the open, the gasket remains fluid, yet seals instantly when parts are assembled. In the Austin Rover factory in Longbridge, the gasket printing process is completely automatic. All the operator has to do is place components into an applicator. Closing the door starts the process, giving cam carriers for S-series engines a gasket containing only 1/5 of the sealant which would be applied were it done by hand. And you don't have to look far to see the results of that automatic production. Loctite printed gaskets ensure clean, dry engines in the Rover 200, the Montego and the Maestro. In the Peterborough plant of Perkins Engines, you can see another automatic application of Loctite gaskets. This time using an advancing head dispenser and rotary table to gasket water pumps for diesel engines. Where the weight and bulk of parts make screen printing or tracing impractical, gaskets can be rolled into place. At the Doncaster plant of J.I. Case, this method is used extensively during the assembly of tractors. Air pressure, triggered by the user, squeezes sealant onto a roller to form a thin, uniform gasket. In service, the gasket must both seal and strengthen the highly stressed joint between clutch housing and mainframe. The same fast method is used throughout mainframe assembly. Liquid gaskets from the roller now also seal axle housing and hydraulic cover plates. But this change was only made after several months of field trials and rig tests had proved that Loctite liquid gaskets were superior to cork. J.I. Case also used the same versatile sealant to seal the external shells of oil seals and to strengthen their retention. And Case even used the same product to secure and seal bolts, preventing leakage past threads tapped into gearbox casings. But this versatility was not the reason why J.I. Case changed from pre-cut cork gaskets to Loctite formed-in-place gaskets in November 1985. Conventional gaskets couldn't endure the loads imposed upon them as the tractor twisted and turned, pushed and hauled. J.I. Case now use Loctite gaskets for the same reason as the earth movers Terex and tank makers Alvis, to gain metal-to-metal seals which add structural strength and increase torque transmission. No traditional gasket can give these advantages, which is why they're no longer used in the final drive of Alvis armoured vehicles produced in Coventry. Development Manager John Radford.
When this project was originally designed, the design incorporated the standard paper gasket seal. Following trials and experience in service, we experienced oil leakages from the joint between the annulus and the stub axle due to this gasket fretting. We introduced Loctite gasket seal, and after extensive trials by the British Army and ourselves, this overcame the problem of leakage and was eventually introduced into service.
An MOD-approved Loctite sealant is now manually applied by a simple syringe that is both container and applicator. With it, a liquid gasket can be applied quickly and cleanly to prevent the micro-movements which caused the fretting between the stub axle, annulus and sunwheel housing. Containing 65 millilitres of Loctite sealant, the syringe provides a continuous bead that can replace 6 metres of conventional paper, fibre or thin cork gaskets. Incidentally, this handy syringe, which is ideal for quickly forming complex gaskets in confined spaces, is the same tool which is widely used for maintenance and repair in the field. Mechanics in several armies now use it to restore their armoured vehicles to fighting trim. There's less to carry, there's less to store. When in service, Loctite seals an OMD 80 oil which can reach a temperature of 150 degrees centigrade, particularly when an Alvis Scorpion is in a hurry. With such a parade of tanks, trucks and tractors, it would be easy to make the mistake of thinking that Loctite gaskets are only for the mobile. A mistake which R.B. Bolton, the mining engineers in Conquest, County Durham, are thankful they never made. Here, the labour of handcrafted gaskets has been replaced by the leisure of liquid gaskets. Cover plates made from unmachined stock are now sealed with a Loctite sealant to flanges that have been roughly abraded with a hand grinder to remove weld spatter, a change which has helped reduce the time of manufacture for a 350-gallon hydraulic tank from 50 hours to just 18. Similar savings have been made during the building of Bolton Dynatrack chainless haulage traction units used to drive coal-cutting machines. The lubricants in the heavy-duty three-stage drop-shaft traction unit range from an EP90 to a power gear oil. But despite this variation, only one general-purpose sealant is used throughout construction. Simply applied and accurately positioned by a standard handgun, this single sealant will form a gasket that never strays out of place during assembly. The contact of mating flanges automatically spreads the sealant into a wide, leak-stopping gasket. And after assembly, any excess is simply wiped away without the need for solvents. This massive example of Loctite sealing power supplies a torque of 30 tons to the drive sprocket of a Bolton Dynatrack. That's the force needed to propel this 40-ton mechanical cutter along the coal face. Day after day, at speeds of up to 30 feet per minute, the cutter hews out 1,000 tons of coal every hour. But at the final proving ground of the coal face, you'll find many examples of Loctite gaskets. At Westow Colliery, 10 kilometres out under the North Sea, for instance, you'll see Bolton's hydraulic supply tanks. And the product Bolton service engineers always take with them. You'll also see Dosco tunnelling machines, such as this Mark IIA road header. These machines are overhauled at the Allerton Bywater National Workshops in the northern region of British coal. It's here that the gearboxes for road headers and dint headers are totally rebuilt. Note that the gearbox halves are split at the bearing centre line. Because the Loctite sealant ensures metal-to-metal contact between the flanges, there's no shimming effect. Consequently, the clamp load on the bearings can be precisely calculated and maintained. The internal filter gave British Coal another incentive to change to Loctite. Pre-dispatch trials showed that excess from previous air-drying sealants squeezed into the gearbox blocked the filter. But excess from an anaerobic product, even the non-drip version used by British Coal, can always be wiped away from the outside and flushed away from the inside, a fact proved by tests at Allerton Bywater. But the ultimate test for machines rebuilt at this North Yorkshire workshop is provided deep underground. As you've seen, there are many uses for a Loctite gasket and many different ways of applying it.
But there are always two questions asked by everyone considering this product. First, if it gives such a strong seal, how do you dismantle the joint? For the answer, let's go back to the R.B. Bolton factory at Concert. Here, their hydraulic supply tanks also eventually return, after several years of continuous service in British coal mines. During reconditioning, the tanks, scarred by their service in the mines, will be completely stripped and all covers removed, proving in the process that normal tools and ordinary methods are all that are needed to break the seal. The second question always asked is, how are the original Loctite liquid gaskets replaced during routine maintenance? You'll find the answer wherever engineers overhaul, repair or service vehicles, plant and machinery. After the original gasket is scraped away or dissolved by a Loctite gasket remover, a new liquid gasket is simply squeezed into place. Because squeezed bottles, tubes and cartridges of Loctite liquid gaskets identical to the product used during the original manufacture are available throughout the world. With one of these in his toolbox, any engineer, anywhere, has the answer to the question, to leak or not to leak.